The precise definitions of right and left limits. Definition. We say that limit of f(x) when x approaches to c from the right equals L if for every epsilon positive there is a positive delta such that f(x minus L in absolute value is less than epsilon whenever x is greater than c and is smaller than c plus delta. Here is the matching definition from the left limit. We say that limit of f(x) when x approaches c from the left equals L if for every positive epsilon there is a positive delta such that the absolute value of f(x) minus L is less than epsilon whenever x is greater than c minus delta and smaller than c. The precise definitions of infinite limits. We will start with limit to infinity. We say that the limit of f(x) equals infinity when x approaches c if for every positive m there is a positive delta such that f(x) is greater than m whenever x minus c in absolute value is less than delta. Here's the matching picture. We know already to observe and to see that this graph is approaching infinity when x approaches c. What does it mean? If I will shrink around the x equals c both sides, left and right, as usual, as we did before with finite limit, then as you can see, there is this y equals m, which can be any positive number, because I would like to recall we will find delta according to the given m, and as you can see, from some point, all the values of the function are more than m. It also means that if I will shrink more about x equals c, then in this case I have like a better m if you want. Now this is the new m, and the function is even greater than this m. We say that limit of f(x) when x approaches c equals negative infinity if for every n which is negative there is a positive delta such that f(x) is less than n whenever x minus c in absolute value is less than delta. So again, if we will choose this n, then this is going to be the right delta, because as you can see, when I shrink around c like that, then really all the values of the f(x)'s are less than n in this stripe. And again, I can shrink it even more and get a smaller number. And now f(x) is less than n for this specific value of the y. We want to show that the limit of 1 over x to the power of 2 when x approaches 0 equals infinity. Here's the definition, and we have to do it now using the definition. So if before, in finite limits, we have to find delta as the function of epsilon, now the delta has to be the function of m. And in this specific case, we have to show that for every m which is greater than 0, there is a positive delta such that 1 over x to the power of 2 is greater than m whenever x minus 0 in absolute value, which is also x in absolute value, is less than delta. Again, we have to find first of all delta as a function of m. absolute value of x is less than delta. So x to the power of 2 is less than delta to the power of 2. But if you look, I need to create 1 over x to the power of 2. So I will take the reciprocal of both sides, and now I get that 1 over x to the power of 2 is greater than 1 over delta to the power of 2. If you look what we have to show that for every m, there is a delta such that 1 over x to the power of 2 is greater than m. So I'm going to assume that this is my m. And now I'm solving for delta. If 1 over delta to the power of 2 is m, then 1 over x to the power of 2 is greater than m. And here, I can solve for delta as a function of m. And I get that delta to the power of 2 equals 1 over m, which means the delta equals 1 over square root of m. M is a positive number, so it's okay to take the square root of m. M should be a really large number, and as you can see, we get really the delta is a small number. In step 2, we have to go backward to show indeed what we need to show, that for every m there is a delta greater than 0 such that 1 over x to the power of 2 greater than m whenever x in absolute value is less than delta. So let's show that. Absolute value of x is less than delta, which equals 1 over square root of m. Then x to the power of 2 is less than delta to the power of 2, which equals 1 over m. 1 over x to the power of 2 is greater than m. But even more, this is true whenever x minus 0 in absolute value is less than delta, because this was the starting point here. And indeed, I proved that the limit of 1 over x to the power of 2 when x approaches 0 is infinity.